Okay.
I don't know where should I put pointing.
Well, it did work.
Yeah. The sound is off.
So well, it doesn't work.
Yeah.
It's working. Okay.
No.
Okay, let's start from the flag.
There.
Okay.
Can you try it again?
I'm ready.
In 2 minutes, you can next time.
It's working.
Okay, we can start. Let me introduce Jan Balitsky, professor from Old Dominion University in the state on GFSS lab. He visited us for 3 months. He will stay here at the university using this MEC program up to December, and some questions or more discussion. We can go to
Okay, first, thank you for the
now we
invitation.
can, okay, you can start.
And this is the title. The talk will consist roughly of 2 parts. First, I will tell you the basics of the Wilson-Line approach to high-energy scattering. And then the second part is what my recent work, I mean 7 or 8 years. Okay, so introduction. What is QCD nowadays? QCD nowadays is, well, combination of 3 things. First is perturbative QCD, which is serves for collider physics. Second, lattice QCD, which describes well, properties of nucleons and mesons. And third, low energy QCD, chiral perturbation theory and models. I will talk about perturbative QCD and more than that about factorization in perturbative QCD. There are a bunch nowadays of factorization. First of all, let me start with a very classical thing, operator product expansion for deep elastic scattering. It's how QCD came into being. It results in famous big lab equations for PDS. Then there is a collinear or Collins-Soper-Stedman factorization. There is rapidity factorization, which I will be talking about, which gives us description, geometric QCD description of small x physics, and recent developments are so-called soft linear effective theory, which tries to combine all the things. Okay, current status of this factorization. The Glove equation, 3 loops, and analog. Linear factorization, 2, sometimes they brag about 3 loops. Rapidity factorization, 2 loops, analog and sketch. I'm not an expert, but I haven't seen an analog yet. Maybe I'm missing something. Okay, so let me compare the linear and rapidity factorization, for example, for particle production in hadron-hadron collisions. The linear factorization says the following thing: parton emits with fraction of the initial momentum x1, another parton from the another nucleon with fraction of momentum of this nucleon x2. They collide and produce particle. Here the diagram corresponds to the Higgs production by gluon fusion. What linear factorization does, it resums the following logarithms. Logarithm of mass of this particle divided by mass of the nucleon. And assuming that log of overall energy to mass of this particle is of order of 1. On the contrary, rapidity factorization, sometimes called KT factorization, resums all the following logs. Log of this x, assuming that they are big, and well, kind of assuming that log of mx to nucleon is of order of 1. The formula looks similar to this, only here logic is like that this nucleon emits parton with KT K1 form, this emits another parton with K2 form. Integration goes over transverse-momentum, then that's why the name KT factorization. Okay, by the way, for Higgs production, only this is important, and the reason is very simple. That for Higgs production in the central rapidity region, x1 and x2 fractions are of 0.01. And we know from the experiments that for such Bjorken X, the Glove formalism works pretty well. So there is no need for small extra summation in this case. If you consider, however, the emission of the particle with M of bunch of particles or mini jets with mx of order of 10 GeV, then this is more relevant than collinear. And from experiment, we know that collinear factorization doesn't seem to work well, for example, for BB production. So some kind of small extra summation is needed. Okay, that was the place of the extra summation in the collinear physics. So there are another experiments like Miller jets, which measure, which can measure and discover this extra summation directly. But for the most famous particle production, Higgs production, collinear factorization is fine, and that's why this kind of summation was never used by some people. Okay, but still we are interested in this type of summations. Something? Maybe put here so I can do it by phone.
Just unplug the USB receiver and plug it again. The USB receiver.
This one.
Okay.
Okay.
And turn on and off and on the pointer.
Pointer. Okay.
Did you use it yesterday or?
Yes.
I can turn pages manually.
Yeah, but the stage.
No. Stop working again.
Yes.
Oh, yes, working.
I will get another one.
Okay. So, is high energy scattering and Wilson lines. Wilson lines is very convenient tool to describe high energy scattering in QCD. What are those Wilson lines? Let us start from quantum mechanics. Well, suppose a particle crosses some region with the potential at high velocity. In the WKD approximation, the wave function is e to the power I divided by h bar times action. Action is given by this formula, and I rewrite that. And if energy is large, I can neglect expand in terms of potential divided by energy, and then I get the following formula, which means that wave function is a free wave function times the space factor. So psi at high energy is free wave times space factor ordered along the line of classical propagation. By the way, it leads to the famous Glauber formula for the total cross-section in quantum mechanics. Okay, what about QD and QCD? Same story. Action is given now by relativistic formula, which can be rewritten in the following way. You need to expand this. You need to expand this once and get the following formula. So the phase factor for the high energy scattering given by this expression, which can be rewritten in the following way. And for QCD, instead of electron charge, you have QCD coupling constant, and A mu is a matrix, therefore this phase factor is now ordered exponential. In this form, it is called Wilson line operator. So let's consider, as example, deep inelastic scattering at high energies. At high energies, particles move along the straight lines, and the amplitude of virtual photon scattering reduces matrix element of two Wilson line operator, which is called color hypo. I think this term was coined by Boris almost 50 years ago. So two Wilson line operator goes by the name color dipole. And roughly speaking, what happens in the following: virtual photons moves very fast, splits into perpendicular pair. Each pair propagates along the straight line and acquires this phase factor about which I was talking on the previous conference. The amplitude then can be written down as integral over this transverse distance or transverse momentum times matrix element of the two Wilson line operators divided by U here between target states. energy dependence of amplitude then is governed by rapidity evolution of these scalar dipoles. Second part, rapidity evolution of scalar dipoles. Well, to this end, let me return a little bit back and tell you that this picture is kind of have in mind a frame of the target. Partial portion is very fast, target is sitting in its place, and you have two very long propagations of work along the straight line. But technically, it's more convenient to sit in the frame of the incoming partial photon. Then what you see? You see that this target with the gluon cloud approaches you at great speed, and that's why it shrinks to the pancake. And rapidity factorization works like that. You say that there is some rapidity divide eta. And if rapidity is greater than eta, I include it in this coefficient function. If rapidity is smaller than eta, the gluons form matrix elements of Wilson line operator. It's a general statement. Particles with different rapidity perceive each other as Wilson line. It is known for almost 50 years and can be demonstrated even formally. So if two particles have very different rapidities, they perceive each other as Wilson line. Okay, then the object here is this Wilson line, but because of the factorization, we integrate all rapidities only up to some cutoff. This is written, this cutoff. Alpha is, by the way, Sudakov variable. It will be explained on the next page, sorry about. So, in the spectator frame, what we see? Well, suppose there is a target nucleon, then we, in the spectator frame, we see boosted nucleon. Boosted nucleon is a pancake. And it is known that propagator can be written down as the functional integral of all the paths, I mean, with like a free functional integral multiplied by exponential along the path. Now the path when we can see the propagation in the pancake field or in the shockwave field, first you have free propagation up to this point. Then interaction with this shockwave and propagation to the final point. Because this interaction is instantaneous in light cone time, it can be replaced by segment of straight line. So there is duality here. In the target frame, you have infinitely long Wilson line from minus infinity to plus infinity. In spectator frame, this is instantaneous, but still it's along the straight line. So formally, you can extend the integration here to from minus infinity to plus infinity. So the picture is this shockwave background is the following: free propagation up to point of interaction with the shockwave, then instantaneous interaction with the target, described by Wilson line, this Wilson line, and then free propagation to the final point. This picture turns out technically to be extremely convenient. Returning to the description of differential scattering, after factorization, we have the following picture. As I explained, these two quarks see the target as the pancake or shockwave. In the leading mode, they just derivative propagators here, multiplied by what we see down, we see the Wilson line operators. Why Wilson line? Because this particle, well, you may say now that this particle is have rapidity very different from the target, and then they perceive the target as through the Wilson line. Of course, it's only in the leading order. There can be also fast another gluon with this range of rapidity. Then the picture for that gluon will look like that. It's an analog direction, and still it perceives the particles, gluons in this side, in this red area, perceive target as Wilson lines. So high-energy accurate expansion look like that. P products of these two currents is integral over transverse momentum, that is 2d1 and d2. The result of calculation of these simple diagrams, which is called impact factor, times trace of two Wilson lines. And in principle, plus analog contribution, which I will be talking about later a little bit. So the next step is how do I know how this depends on, returning to that. How do I know the energy dependence? The energy dependence is governed by the dependence of this two Wilson line operator called dipole on the rapidity cutoff theta. And I will show that evolution equations for these colored dipoles look like that in the leading order, and I will show you an analog kernel later. By the way, linear part of the analog kernel is analog KL, which was calculated by Balitsky and Badin, committed to Apollonia like 20 years ago. How to get evolution equations for colored dipoles? The same ways you get the Dirac evolution equation for splitting function. You say, okay, I have here gluons with rapidity up to eta 1. I integrate over a small region of rapidity between eta 1 and eta 2. I again get Wilson line operators because times some kernel. Why Wilson line? Because the rapidities in this eta 2 is still different, very different from target rapidity. So these gluons perceive target as Wilson lines. It reduces to Wilson line operator. And well, the result of integration of this region of rapidity gives you evolution kernel. Of course, there are too many gluons, too many coupling constants. But in the leading order, it's only two. In the leading order, let me return back. You have only one gluon going down and returning up. So in spectator frame, well, spectator here, we forgot about spectator, but still in the frame where this target is very fast, it looks like that. So, beginning of the evolution, Wilson line colored in blue, emitting gluon and absorbing gluon, and it goes through the pancake of the target. And now, result of the evolution, you need to count Wilson lines inside this red top wave. So here will be the same Wilson line, here the same, here gluon, very fast, gluon Wilson line. One Wilson line in the adjective presentation is equivalent to two Wilson lines in quark representation. So what you get after the evolution, you get nonlinear equation. You have two Wilson line, one dipole in the beginning, and then you will have two dipoles, this between this, and between again this and this. The calculation of these diagrams itself is very simple because these guys are purely perturbative gluon propagators, nothing very difficult. And the result of calculation is the following. It is convenient to subtract one from the color dipole and introduce this calligraphic U. And then in terms of this calligraphic U, the nonlinear equation looks like that. Let me mention it was derived first by me, but I should confess I didn't realize the power of this equation. Yuri Kovchegov derived it 3 years later and recognized the power. Alternative approach goes by the name Jim Walk. They talk about not evolution of the projectile, but evolution of wave function of the target. The results are the same. Some words are a little bit different. Okay, so what is the meaning of this equation? By the way, the first 3 terms are linear equation, which describes leading logarithmic approximation for deep analysis scattering into derivative QCD. Leading logarithmic approximation, let me remind you, is coupling constant much smaller than 1, but coupling constant times corresponding log of energy of rapidity is ordinary 1. And if kind equation rests sums all such laws. Then what is this nonlinear term? Why is it important? I would like to say that it's leading log approximation for deep analysis scattering in semi-classical QCD. Meaning, suppose we have large nucleus. Then in addition to these 2 parameters, you have a new parameter, atomic number to the power 1/3. It can be of order 1, and then the FKL is not enough, even on derivative QCD, you need the full nonlinear equation. So this is, let me just mention that current status is we have now NLO, this nonlinear equation. It was calculated by Gianni Kirilli and me 15 years ago. And let me flash, just to brag, let me flash some diagrams for this NLO. Of course, the real number of diagrams is like 5 times this. The calculation is was difficult because there was no, you cannot use the tools which are invented by people who calculate amplitudes in, well, say on the collider. When they calculate, say, jet production. Because you need here the specific situation that there are cutoffs which you cannot use, for example, the result of some calculation and plug in it directly into this calculation of the analog kernel. You need to do it by hand. At least I don't know the efficient way. Okay, we calculated like 100 diagrams, and this is the result. This is the kernel, the leading order, and below you have, because its equation is nonlinear, and below have 3 dipoles here and more complicated combinations. And the kernel is made from logs of the so-called conformal ratio. For QCD, it's combination of the part which depends on D, which depends on this running coupling constant. And there are 2 conformal parts. One is exactly as an n equal to 4 superannuals, which was calculated later. And there is one more contribution, which is conformal, but not part of n equal to 4 calculation, which is kind of strange, but, well, so life is like that. Just to mention, linearized kernel reproduced the known result of forward analog FKL kernel obtained by Fadin and Kamichich Apolloni in 98. Okay, so that is last thing which I need to mention with the analog. That when you write down even leading order equation, you have a problem because what alpha is here? What is that? In the glove, no problem. It is determined by Renorm group. In the KLPK of the light, it is you need to find out this argument of coupling constant. We used with that was done by Kovchegov, Weigert and me. we use BLM or a normal approach. And the idea of this BLM is very simple. You calculate this bunch of diagrams with the quark loops, and then say, whenever I see to have synapse from this bubble, I promote it to the whole B coefficient, which is 11/3 and C minus 2/3 and F. This approach was advocated by Brodsky, Lepage, Mackenzie, so it is sometimes called the BLM approach. Okay, the result for the argument of coupling constant is the following. You can write in some different ways. Bottom line is the argument of coupling constant is given by the sign of the smallest dipole. And this kind of equation, which goes sometimes under the name RCPK, is widely used nowadays in analytical and numerical solutions of the big equation. This concludes the first part of my presentation. Second part will be about this kind of classical results almost 20 years ago. The third part is about TMD factorization. What do these words mean? TMD factorization, TMD is transverse momentum dependent parton distribution, which enters your formulas when you have, say, particle production with the transverse momentum. You don't integrate over the transverse momentum of produced particle, you just keep it smaller than invariant mass. This is recently rather popular activity because we have, well, first of all, because of the LHC, and then, for example, BB pairs at LHC should be described by this. And of course, because of the future electron ion collider. Anyway, what is TMD factorization? People write down formula like that after John Collins. The differential cross section. This is the production of the particle, is Q4 and theta, is given by the following formulas. It's integral over transverse momentum of these two TMDs, which are fraction TMD. The first TMD is density of the parton F in the hadron A with a fraction of momentum XA and transverse momentum vector. This is the same for the second hadron. The coefficient is determined by cross-section of these two particles going, say, for Drell-Yan in mu plus and minus pair. The classical example is Drell-Yan process, with Q being the mass of Drell-Yan pair and its production by Bjorken. Let me stress again that TMD approach is relevant when the transverse momentum is much smaller than the invariant mass of the particle or combination. Classical example before that. This is kind of my long-term project. TMD factorization valid at both small and moderate x. As I told you in the beginning, at moderate x you have collinear factorization, at small x you have rapidity factorization. But suppose you are somewhere in the middle, like for EIC collider, which should you use? And it's nice, would be nice to have the formalism which interpolates between these two factorizations. Okay, I think the TMD formula is is suited for this transition with some thinking. Okay, so what people do? These quantities, they are defined with cutoffs. The dependence of the cutoffs cancels in their product order by order in coupling constant. At moderate XA and XB, people use CSS or SCAD approach. These TMDs are defined with a combination of ultraviolet and rapidity cutoff. At small x, this KT factorization approach, the TMDs are defined with rapidity only cutoff. I would say that it's impossible to extend CSS to small x. Just Koenig-Silberstein factorization is based on the following idea. All the momenta you consider diagram, all the momenta in that diagram are multiplied by some large number. So if you have, this is suited for fixed angle scattering, and small x means means range limit when one variable is very large, S, for example, energy, and transverse momentum is fixed. While CSS considers the case when the energy is large and transverse momentum is large, they both go to infinity. Therefore, this method cannot describe small x fields. Scared in principle can. Recently, I saw the papers where they reproduce a lobby file from Scared. Scared is trying to be this combination of CSS and rapidity, but well, they are not there yet. They cannot reproduce, for example, an lobby file. On the other hand, it is possible to study TMD factorization at moderate x using small x methods. It was, well, we have a bunch of papers in collaboration with Andrei Tarasov and Giovanni Chirilli. For example, I have calculated recently full list of power correction for Drell-Yan hadronic tensor. They are not obtained yet by CSS or Scared. So here, I think rapidity factorization, it was not invented for the calculation of power correction at moderate x, but it turns out that it works and it was more quick than those guys because they are not paid. Okay, now let me remind you, I will be talking about 5 minutes about Drell-Yan hadronic tensor. Let me remind you the diagram for the Drell-Yan scattering, this mu plus mu minus, so E plus and minus pair. And hadronic tensor is cross section of the product of leptonic tensor and hadronic tensor. Leptonic tensor is kind of trivial. Hadronic tensor, you need to calculate it in QCD, where J mu is either electromagnetic or Z boson current depends on your energy. If your energy is large, like at LHC, you need to take into account also Z boson current. For the electromagnetic part, electromagnetic current, there are 4 tensor structures, which are known again for 30 years. And to find these tensor structures, we used with Andrei so-called, we used rapidity factorization in the following sense. Take any diagram and separate all key gluons and quarks in 3 parts. Projectile fields with the fraction along the target very small, target fields with the component along the projectile very small, and central field is whatever is left. The result of the integration, functional integration of central fields in the background of projectile and target fields is a series of TMD operators made from projectile or target fields multiplied by powers of 1 over Q square, just because of the dimension. If you have X-ray mu in your operator, it must be divided by something with dimension. And the only thing with dimension is 1 over large Q invariant mass of Drell-Yan pair. There is a problem, well, not problem, but the TMD factorization formula for the Drell-Yan hadronic tensor look like that. There are several tensor structures for them electromagnetic currents, and people write down the following formula. There is, however, a problem with this equation for 2 of the 4 tensor structures. These 2 guys are determined by leading twist quark TMDs, but another 2 start from power corrections, which are determined by quark-gluon TMDs. The power corrections of order O1 and Q were found more than 2 decades ago, but there was no calculation of power corrections of 1 over Q square until recently. Let me one technical thing. Structure TMD factorization formula in the coordinate space. This quantity is written down as integral over to longitudinal fractions of the, if it's coordinate space, the transverse coordinates are fixed, they stand here in the formulas for TMD. This operator O projectile TMD operator with the cutoff goes from this diagram. You see that here I include only gluons with some cutoff, and therefore all the operators here will be with this cutoff. Same thing, target TMD operators have the cutoff of the fraction of this momenta in the target direction. Just notations. This is any gamma matrix, can be any, and this is standard notation for the straight line gauge link. Convenient notation is like that. This part of Wilson line gauge link goes to minus infinity in light-like direction, and it's located at zero, fixed zero. So this is the goal. Get such formula, and intermediate step, look here, there are matrix elements between quadrants everywhere. The intermediate step should be calculation of this coefficient. Let me remind you how we have done in deep elastic scattering. We write down formula that T product of two currents between, say, proton states is parton density times coefficient function. Parton density is matrix element of light ray operator between these nuclear states. And to find coefficient function, you need some calculation. You cannot calculate with the nucleon. So what people do instead, they calculate coefficient function matrix element with the target state being gluons of works. And then, because you know how to perform direct coordinate function, you calculate this coefficient function times matrix element of light ray operator between nucleon states. So the stage of the calculation of the coefficient function is done in, well, let me say, in the background of free quarks and gluons. Similarly here, intermediate step is so-called double operator expansion. There I write down formula for the product of two currents. And this separator equation, and to find coefficient function, I consider so-called matrix element of the indisputable background field. It turns out, well, for deep elastic scattering, this background field would be the free gluons. And then, if you consider the expansion of the background field into coupling constants, you get normal diagram for deep elastic scattering, for example, box diagram with two gluons. But here situation is more complicated, so you need background field more complicated. And this background field is convenient to You can, in principle, choose whatever background field. You need to be sure that you took into account, you found all the operators and all the coefficients. That's why you are free to choose your background field. But if you made a mistake, you miss half of the operators. So it turns out that suitable background field is solution of classical Young-Mill equation with boundary condition at the remote path. The field is a sum of projectile and target field. So instead of calculation of this between hadrons, like was here, that's what I need, but I cannot calculate with hadrons. Therefore, I am calculating in the background of this classical field. Method of finding this classical field. Start with the trial field, which sum of the projectile and targets, and correct by computing Feynman diagrams with the sources, because these are not solutions of classical equation. There will be sources, just the effect of the action, and they serve as, sources of for this correction field. For example, this is correction field for the work. What you calculate is a bunch of the following diagram, quark line. These are projectile fields, these are target fields. In the middle, you have field which is neither central field, which is neither target nor projectile, and you need to calculate side diagram. Of course, in practice, you need to calculate a couple of them, and but there is one important thing. The solution of such Young-Mills equation in general case is unsolved problem, goes under the name plasma or scattering of two-color gas. What do I mean by general case? You have a situation when you have projectile and target colliding at time minus infinity. You know that field, there is something happens, and you have in the beginning of the collision, you have new classical field. And there were many attempts to calculate it analytically, but it's not yet solved. Some people solve this numerically, and numerically you can have a look at this classical field. It goes in the papers of these people, it goes under the name plasma, which was coined by Larry McDermott. Fortunately, for our case of particle production with this parameter, we can use this small parameter and construct the approximate solution. If this parameter is small, what happens that in those diagrams, well, here there is some propagators, yes. It turns out that that propagator is a retarded propagator for the specific reason which I don't want to mention right now. But what happens, because of this parameter, you can expand the propagator in ratio of perturbative momentum to transverse momentum to longitudinal momentum. And then the dynamics in transverse space is trivial, and these guys go into, let's say, gluons, F-minus, something like that, of quarks, not quarks, but extra gluons in the quark operators. It's important that if you have only transverse, only longitudinal momentum in the numerators, then fields are either at point x or at the point 0. And this goes into d quark square for quark operator applied to quark operator, which gives extra F mu near the quark operator. Anyway, this gives power corrections. This is power correction because it will be of the order of q per square, and this is of order of this q square. Power corrections have the following general form. It's leading twist times 1 over q or 1 over q square. In principle, there's a different orders of NC. It's interesting that almost all QG stands for glue. Quark gluon quark TMDs, not suppressed by 1 over NC, are determined by leading order TMDs due to the equation of force. For example, this is TMD F1. E2 is like it's my notation. It should be here gamma plus. Sorry about that. But anyway, that's so-called TMD F1. And power correction, if you have here a slash, which is gluon field in light gauge, then due to QCD equation of motion can be rewritten like that. This fact was known for a long time after the paper of Mulders and Tangerman, which they calculated this correction, but didn't calculate that. I don't know why, maybe the machinery was not developed enough at that time. I have made this calculation of 1 over q square correction, and I will present you the result for the Z-Boson production. In their experiments on LHC, in this kinematical range, where Q curve varies from 0 to 120 but our analysis is valid when Q curve is smaller than invariant mass Q, and in the central region of rapidity. So the power corrections are small but sizable. Angular distribution of Drell-Young vectors in the Collins-Topper frame is parameterized in terms of eight parameters. They are called angular coefficients, and I have made a back of the envelope estimate. Took only one TMD. Used factorization hypothesis for this TMD that it is product of something depend on X, which is basically PDF, times something depends on K-curve, and calculated the integral over K-curve in the leading logarithmic approximation. Back envelope estimate, it turns out that only two are non-zero in this estimate. A0 and A2. All others, if you use this hypothesis, are just zero. And well, if you look at the experimental data, they are smaller than A0 and A2. And for A0, I have the following estimate with zero parameters, nothing here, just, well, no parameter at all. And that's my curve. That are the data from CMS and Atlas. For A2, the accuracy is a little bit worse, but it's still okay because all my calculation was with 1 over NC accuracy. So the accuracy here is 1 over NC. And it is funny that back on the envelope estimate gives, right, is comparable to the experiment. So this method of calculation of power correction works, and next part, last part, is rapidity factorization and rapidity evolution of TMDs. I will try to be quick. Rapidity on the cutoffs means that these TMDs, this and this, will depend on the cutoffs. The picture of the fields is like that. The fields A, these fields, they have a small fraction of the target momentum. B is smaller than some cutoffs. Similarly, A fields, not that this is A, this is B, they have small fraction along the target. So did I do it correctly? Again, this projectile field B is small, but Yes. And for projectile field B is small. For the target field alpha, which is component along PA, is small. And the rest is C fields. But the coefficient function is integral over C fields. It will depend on these cutoffs, both of them, sigma target and sigma projectile, and the dependence should cancel with in physical amplitude with the dependence of TMDs on these cutoffs. There is a subtle point here, which I just mentioned, that there is intersection between A and B fields. You can have a gluon, for example, which goes like that. And it will be both A and B. And there are two types of gluons here, soft or glauber gluons. And it is known that it is demonstrated in papers by John Collins that glauber gluons cancel out, and cancellation of soft gluons I traced, I calculated that and showed in my paper. So to speed up, one important thing, unfortunately, before speeding up. The difference between rapidity only cutoff and cutoff used in CSS factorization. This is the typical diagram for TMD. Work, and this not half of the Wilson line, gauge length going to minus infinity. If you write down the very first diagram for this, you will see that it is divergent. Now, if you impose cutoff, rapidity cutoff, you will see that it's convergent, and rapidity cutoff here is easy to visualize as the point splitting. You separate Wilson line from the quark. Of course, it's not gauge invariant, but I have shown that violation of gauge invariance power correction, which we neglect in this calculation because we are after logarithmical evolution. So the typical integral is written here in full glory, and you have the following integration. If you are using CSS approach, you regularize rapidity something like that, and the result will be product of two logarithms in ultraviolet log, where mu is ultraviolet cutoff, and rapidity log. If you use rapidity only cutoff, same integral, but regulated in a different way, and the result is log square of the rapidity cutoff. That's why the formulas for CSS factorization and rapidity factorization are different. Of course, you can, in principle, you can reconcile that. If I will have a good student, I will give him a task to consider this analog calculation both in even leading order in rapidity factorization and CSS factorization and compare. But unfortunately, I don't have that good student here. Okay. Rapidity evolution, as I told you on that diagram, I need to calculate integral of this to find coefficient function, and I need to find the dependence of on these cutoffs. Both coefficient function and TMD will depend on the cutoff, and I need to find the evolution equations for TMD. I will just flash you because time is running short. I started at 35, yes, 5 minutes ago. There are diagrams for the rapid evolution of TMDs. We have calculated this with Giovanni and wrote the following. This is the evolution equation with respect to cutoff multiplied by size of this TMD for technical reasons. And the solution has the following form. It's funny that, well, it is conformally invariant because it's leading order in QCD, and leading order is almost conformally invariant. Argument of coupling constant for this TMD, the same story as for dipole evolution. We know the evolution equation, but what stands here? Alpha S of what? And to find the argument of coupling constant, we again turn into BLM approach, and the result is BLM optical scale is logarithmically halfway between transverse momentum and energy of TMD, which is for me was kind of surprising because when I learned pedagogy QCD many years ago in Leningrad at that time, I was told that everything coupling constant always depends on something transverse. Well, it looks like not always here. It is halfway between transverse and longitude. Now, one loop coefficient function, integral over these C fields. Again, you need to calculate diagrams. You write down formula for NLO coefficient function. It is diagram minus matrix element of the TMDs. Why it is so? Because you write down first in the leading order just these two TMDs, but in the next leading order as in deep inelastic scattering, you need to calculate diagram and subtract matrix element of the operator in the next NLO order. The diagrams, I will just let them. There are diagrams for this in the ground fields of this type and this type. And subtraction is TMD matrix element with regularization. The result of the calculation, it was rather lengthy, but still the result is simple. There are transverse size and cutoffs. As is energy, these guys are cutoffs, and these are fractions of the longitudinal momentum of the TMD. And a solution of TMD evolution equations compatible with this first order result. This is first order calculation. But it needs to be compatible with TMD evolution equations. And it is easy to check that very simple guess that in general coefficient function exponential of the first order goes through the equations, through the evolution equations. So the result is like that. Very simple formula. For the forward case, which is particle production by gluon fusion, it has the following form. So again, ingredients are transverse size of the TMD. It's Fourier transform of this is Q of emitted particle times string which depends on the cutoff. And finally, what is its formula useful for? The right-hand side of the evolution formula doesn't depend on the cutoff as long as the cutoffs are larger or equal to the thing. It's Q bar squared divided by longitudinal fraction. Thus, the result of double log Sudakov evolution, which I obtained, is this. The question is what to do with this result. This result is universal for moderate x and small x. The difference lies in the continuation of the evolution beyond Sudakov region. There are two possibilities. If Bjorken x is of order of 1, after that you need to evolve the glove type from this my cutoff to final cutoff, which is m nuclear squared divided by s. Then there is a room for the following resummation of single logs. Here there is a double log, but the glove type is single log. On the other hand, if Bjorken X is much smaller than 1, then there is a room for BFKL evolution between this cutoff and the final cutoff for BFKL physics. And it corresponds to summation. If you divide it by this, you have alpha s log of x. So this double log Sudakov formula is universal for small and moderate x. Then you need to think what there are two cases. And for this case, the final result should be the same as for CSS approach. But it has not been checked yet. Because there is a hard to match this. I'm thinking about this, but didn't solve this problem yet. Okay, conclusions. Rapidity only factorization is the most convenient tool for high energy QCD. Current status and the law for BFKL decay evolutions, and the low evolution and the low impact factors for various processes. By the way, for n equal 4 super mils, Simon Karan-Hood calculated, or better say, found the way to get the result from the calculation of non-global logs for the n equal to 4 super mils and conformal symmetry. Still, that gives a hope that an analog decay can be calculated, but we are not there yet. Impact factors for various processes, it is from shockwave approach. We have leading order and analog calculation for many cases. And there is even the following speculation, which is very popular right now. It is, people say, okay, the product of impact factor times maybe summons of Wilson line theory. Let us calculate the impact factor with the individual approximation and multiply by 2 Wilson by color dipole in the BFKL approximation. It's of course not logical because you don't have the exact matching here, but still people use it. It's very popular approach. They just use some cutoff and say that it's much more logical cutoff between BFKL and the evolution. Then for the second part of the talk, rapidity only evolution with BLM prescription gives the same universal formula for the evolution of quark and gluon TMDs, both for moderate and small ends. And rapidity factorization at one loop level gives a double type double logs for both small and intermediate x. And as I told you, previous transparency, the devil is in the details after that. When you finish double logs, you have single logs, which are quite different from moderate x and small x. And the last thing is, thank you for attention.
Okay, thanks for the presentation. Question? Okay, can I do a small question? You talk about this decay equation with the running coupling.
Yes.
In this case, you are considering that the running coupling is what's happening in the infrared. This is the lambda pole, or you introduce some specific condition about this?
Yeah, you can get into that. No, people are trying to put it in front somehow. So they are not. Formally, you get what I wrote on the blackboard, but when.
No, so it must, you take the equation, when you go to the saturation regime, you still have this.
Let me try to click back to the formula.
Page 22.
22, a lot of clicking.
Yeah, that is the general expression.
So formally, this is what will happen. If you, this is denominator, you don't care, in the numerator you care, yes, about Z13 going to 0, for example. But here, 1, 3 goes to 0, that cancels. That cancels this, and this is logarithmical divergence. Well,
Yeah, probably depends from the size of the dipole or in which one.
yeah, I think
Region are you
etymologically
discussing
people use something like that. I don't know, there is some etymology, but I didn't look in their formulas.
Okay.
But that's very important.
No, and when you talk about this cutoff, when you said that is your result is universal, usually you can use another cutoff or restriction. You use this exponential cutoff in order to consider.
I want formula valid for both for transition between small x and moderate x. And for now, the price to pay for that is that I need to make it. For example, I want to compare to CSS evolution at moderate x. They have the whole evolution from this combination of double lobes and single lobes. I have at the first this step only double lobes up to some point, then I need to match to single log evolution and compare to CSS. I cannot do, I'm thinking about that, but this paper is 1 year old, so I haven't solved that problem yet. But it needs to be solved in order to write down formula for cross-section, which needs to be solved. I cannot write down formula for cross-section yet because I didn't measure to the Dukov evolution and to Gilbert or to the Kyle evolution. It's not done. Therefore, I cannot write down formula for cross-section. But I think it's the fact that it's universal for small and moderate x, it's interesting. Okay.
Question, Tom?
Yeah, what observables you can predict with this approach? For example, I think that is it, hadron collision. For example, total cross-section, elastic cross-section, but
well, for example, production of B and TB pairs for LHC. It is perfect case. The mass of the particle is around 5 GeV. And then CSS factorization gives you log of 5 GeV to 1 GeV, which is log of 5. And BFL gives you factorization of this x1 s, which is square root of s, which is square root of 7 PV divided by 5, yes. So compare. For example, this, but to do this, I need, in this case, it's BFKL case, so I need to match it to BFKL evolution for the TMDs, so to say. So that still work needs to be done, but yes, I have in mind process like that.
There's a lot of information. A lot of information is. I would like if you can explain, if you have time, the image, because I didn't see the image that you show, in which you form when you put A intersection B. If you can explain in better way, I think you can please go forward the slide, please. In the this block.
I cannot draw.
Yes, you can draw. Yeah, here.
Where can I draw? Blackboard, yes. For example, if you have down, something happens, okay.
Yeah.
But you can have a gluon which goes like that. And not take part in this. You can have a gluon which goes like that. It will be in this classification, is right here. And for example, BFKL balloons, if you consider simply cross section without catching on this, it will be just BFKL balloons. And in this, depending on their transverse momentum, if the transverse momentum is of order of mass of the nucleon, they call Glauber balloons. If the transverse momentum is extremely small, it is soft balloons cancel. With Glauber balloons, it is the story. And in the papers of John Collins, it is written that this guy cancels with, let me try to, with this. It goes around. So this gluon cancels with contribution of this gluon in the cross section. Okay, it is, well, CSS claims that it's proof. I know that many years ago, General Allen was trying to say that's not quite right, but I think he gave up. But it was in the 90s, so long time ago.
Okay, any question, comments? There is coffee for the audience in the case that you can continue.
Coffee machine upstairs is broken. But,
Oh,
at least the ladies told me no coffee. I don't know what it means.
no, but there is coffee there.
Okay, from the audience, perhaps.
Wait a minute, let me.
Okay.
So we can see this. Any question from the audience? Or is, I don't see the Zoom now. No. Nobody. I don't know.
Okay,
Wait a minute.
I hope Boris will come in person at some point.
Yeah, okay. But there is no question on the audience at the moment. Okay, we thanks for the people here in Zoom. We're closing the meeting now.
Okay.
Thank you. There is coffee.
Thank you.
Okay, bye-bye.